The Parker Solar Probe created history by becoming the first spacecraft to touch the Sun. It passed through the Sun's upper atmosphere, known as the corona. Temperatures in the solar corona can soar up to 1,000,000 degrees Celsius. It's the hottest region of the solar atmosphere and is about 15 times hotter than the surface of the Sun. But the critical question is, why didn't the Parker Solar Probe melt when it touched the Sun? No metal can withstand such high temperatures. So, how did Parker manage to survive after plunging into the solar atmosphere? Well, a part of the answer lies in the solar corona itself. The fundamental aim of Parker was to study Sun's corona. Corona, a Latin word for crown, is the outermost layer of the Sun. It consists of plasma and extends millions of kilometers into space. Usually, this layer is hidden in the glare of the Sun. However, it can be easily seen during a total solar eclipse and through a coronagraph, which blocks direct sunlight from the Sun. It is a mysterious region of the star because it's over 15 times hotter than the surface of the Sun. The laws of thermodynamics tell us that heat cannot flow from a cold body to a hotter one. So why is the Sun's surface at around 5,800 degrees Celsius and the solar corona at over 1,000,000 degrees Celsius? There may be an unknown mechanism that's heating the corona. Although the corona has a high temperature, its particle density is very low. That's where the concept of heat versus temperature becomes important. Temperature measures how fast particles are moving. On the other hand, heat represents the total energy these particles can transfer. So even if particles are vibrating tremendously and have a high temperature, if there are very few of them, they won't transfer enough energy. As a result, they would correspond to lower heating. It's like putting your hands in a heated oven and a bowl of boiling water. Your hands can stay for a longer period in an oven without getting much heat. That's because the particle density is lower than the boiling water bowl. For Parker, this concept of heat versus temperature is the backbone behind keeping it safe from melting. Since the corona's density is lesser than the visible surface of the Sun, the spacecraft encounters fewer hotter particles. As a result, it doesn't heat as much as it would in the case of the visible surface. Eventually, the Sun-facing heat shield only gets heated to 1,400 degrees Celsius or 2,500 degrees Fahrenheit, even while passing through an atmosphere of several million degrees. But still, even 1,400 degrees Celsius is a lot. For reference, the temperature of volcanic lava lies between 700 to 1,200 degrees Celsius. So, how does Parker tackle it? The answer is in its Thermal Protection System, or TPS. It comprises a shield made of carbon composite foam sandwiched between two carbon plates. The shield is 2.4 meters in diameter and 4.5 inches, or 0.11 meters thick. Even though it's thin, it can withstand up to 1,650 degrees Celsius and allow Parker to maintain a temperature of 30 degrees Celsius. In addition, special measures have been taken for wiring. The team grew sapphire crystal tubes to suspend the wiring. The wires are made from niobium, with a high melting point of 2,470 degrees Celsius. Parker's solar probe is not only studying the Sun, but it is also being powered by it. However, as the solar panels get closer to the Sun, they might get overheated. So to keep things cool out there, the spacecraft circulates a single gallon of water through its solar arrays. The water absorbs heat as it passes behind the arrays and then radiates that heat into space as it flows into Parker's radiator. Finally, the heat shield edges are accompanied by 7 smart sensors. If any of these detect direct sunlight, they alert the central computer, which directs the spacecraft to correct its position. This way, all the components are safely protected behind the heat shield. So this is how Parker is gathering a wealth of information without melting. If everything goes as planned, the probe will send data from within 6.16 million kilometers of the Sun's surface by the end of the mission. This would reveal the solar secrets at depths that have never been reached before. If you enjoyed this video, make sure to follow our page for more.